3, 2, 1. Okay, we're doing it again. Math 2070, the online section. Alright, let's now get changing. Changes. Alright, so let's say I've got a vector space, and I have two bases. As we discussed last time, the bases have to have the same number of elements. So, for any element in the vector space, we can form the coordinate vectors xb and xc, and note that these things have to both live in Rn. We now know that because we know that any two bases will have the same number of elements. So we know these coordinate vectors are hanging out in Rn, both of them. So, naturally, I would like to establish some sort of relationship between these. Because it'd be great, because then I can have a mechanism that lets me, change between the bases. Hence the title. All right. Now, since this is an element of Rn and that's an element of Rn, we're expecting a matrix that's probably an n by n that would connect the two of them. All right. Now, how are we going to do that? Well, it turns out it's kind of easy what you need to set up, but the justification for it takes a little bit of time. So let's get the justification in. So let's follow our nose on this. If you take an element of your vector space, well then its coordinate vector with respect to b, I can create this linear combo. Right, again, that's what the coordinate vector is. It's just the scalars needed to take our element x and scale and add them up with our basis elements. Now, each one of the basis elements, because it lives in the vector space V, has a linear combination with respect to C. So each one of the basis elements has a coordinate vector with respect to the other basis C. Now note each basis element has one of these corresponding with it, hence why we have the double indexing going on. Right, there's n scalars for each k. All right. Now, what do we know? Well, we have these equations for b. Let's plug them into this equation for x. There it is. Now what am I going to do? Well, hopefully what immediately jumps out at you is that, well, now I can get the c's together. And if I go ahead and do that, I've got these expressions up here. But now note that these are the scalars associated with the basis c that give us the linear combo for x. So in other words, each one of these are the things that live in the coordinate vector for x with respect to c. All right, and hey, I can pull these apart because I've got an alpha in each one of these. So if I just write that as a column vector and all the way down, write each one of these as a column vector there, we hopefully immediately recognize that, hey, wait a minute, these are the coordinate vectors for b with respect to c. And what was the alpha again? Well, this was the coordinate vector for x with respect to b. And, oh, hey, look, I have a linear combo of vectors. I should probably make a matrix with these as the columns. Indeed. So the change of coordinates matrix from B to C, and yes, this is the notation for it, is the matrix whose columns are the basis elements of B's coordinate vectors with respect to the other basis C. Right, and that makes sense if you're thinking about what this should be doing. Changing B to C will take the elements of B and convert them over to C. And as we just justified, we know that multiplying the coordinate vector with respect to B with respect to this matrix, we know it has to equal C, because that's precisely what that matrix multiplication is equal to right here. All right, beautiful. Now, even more beautiful is that we recognize that this matrix has to be invertible. Its columns have to be linearly independent. The B1 to Bn are linearly independent, so its coordinate vectors are linearly independent. So it's an invertible matrix, and multiplying its inverse over then gives me, oh, hey, look, a matrix that multiplies the coordinate vectors with respect to C and converts them into the coordinate vectors with respect to X. So in other words, the inverse of this one is the change of coordinates matrix from C to B. That easy. That easy. Quotes around that. But anyway, so there's the justification for why this is the right thing. This is the matrix that will let us jump from one coordinate vector to another. Now, with that said, now that we've justified its existence and what it does, let's look at some fun problems. In fact, I've got 3 of them for you. All right, so here are some vectors, b1, b2, c1, and c2. note that these form bases for R2. Not too hard to verify that these are linearly independent and thus have to be bases. Because there's two of them, and we know that R2 is two-dimensional, so they have to form a basis. If they didn't, we can enlarge them to a larger linearly independent set, which we know can't happen in R2. Now, something I can do, of course, is create the change of basis matrix that takes the coordinate vectors with respect to B and create the coordinate vectors with respect to C. And the equations those will satisfy are the following. So you have two here that you can solve if you so want, but we can pull a little trick and solve those simultaneously. Right, so note it would ultimately boil down to solving these equations, and we can do it simultaneously. So take the matrix that on the left here, you've got the vectors for the matrix for the basis C on the left, and on the right, you've got the basis for the matrix for the elements of the basis B on the right. Now, if you ref it on the right here, what you'll get is indeed the change of basis matrix from B to C. Right, so the C matrix, the C basis was on the left and the B basis is on the right, and we know that the coordinate vector for 7, 5 has to be the thing, so that when you multiply by the elements of the basis will give you the 7, 5. That will give you the linear combo you need to get this as a linear combo of those bases. Likewise here. So you want to solve these simultaneously. So that's what you do. And note that gives you that. So hey, you can compute the change of coordinates basis for two bases out of Euclidean space by just setting up a augmented matrix and doing the echelon form. Right, and again, note the notation. Like I said, it's kind of a little weird, but it is kind of letting you know what to do. You gotta put the stuff with C on the left and the stuff with B on the right. And note that once you have this, you don't need to do it again, you just need to find the inverse of this to get the other one. And there it is. Hey. Nice and easy. Alright, so there was problem number 1. Let's make it a little more abstract this time. So let's say I have two bases, B1, B2, C1, C2 for some vector space V. And let's say I know a little bit more. Let's say I know that B1 is that linear combo of the elements of C, and B2 is that linear combo of the elements of C. Note I told you something. I told you the coordinate vectors for B1 with respect to C, 6, -2. And I told you the coordinate vector for B2, 9, -4. So I can create the change of coordinate basis matrix, right? I told you what the linear combos were. You didn't have to compute them, right? In the previous problem, you had to, because I didn't tell you what they were. I just gave you the basis elements. But in this case, I told you what the linear combo needed to be, and so we've got the change of coordinates matrix right here. Now, if I gave you a vector written as a linear combo of the elements of B, I told you the B coordinate for it. And so I can compute the C coordinate for it by multiplying by that change of coordinates matrix. And now note, this told me that, hey, x is equal to this with respect to B1 and B2, but I now know what it is with respect to C. Doing a little matrix maneuvering. Pretty cool. And you can double check that this has to be right in this case, because I actually have the formulas for B1 and B2. Neat. Alright, cool. Good stuff. So there's problem number 2. Now, well, let's get problem number 3, and let's go over and hang out with our good friend, the polynomials. Alright, so let's look at P2. Alright, B over there, I claim is a basis. You can verify it. I'm claiming it's one. You can double check. Now, C here is our usual standard basis for the polynomials, 1t and t squared. So note that the C coordinate vectors for these polynomials in the basis B is pretty easy to compute, and thus that gives me our change of basis matrix, because these are going to be the columns of them. Alright, so this takes the elements of the basis B and converts them over to how things work in C. The inverse of that matrix I've computed, it's this. So now I have a way of converting from the standard polynomial basis to this new basis B. So I can find the b-coordinate vector for any polynomial. So for example, if I've got the polynomial negative 3 6t minus 5t squared, if I want its b-coordinate, I multiply this matrix by the c-coordinate, and the c-coordinate is just the standard coordinate for the polynomials, which is just the coefficients. And again, as always, you can double check that this is right by actually taking these and scaling and adding up the polynomial basis b. And if you check it, it'll indeed be right. Alright, and there you go. Changing your bases just amounts to making this matrix, and that's the story. Alright, so I'll see you in the next video.